Balaji. He worked in Singapore and Australia as a technical consultant for about 2 years. In India, he worked as an assistant professor in the Department of Aeronautical Engineering for Hindustan University about 4 years and as an instructional designer for 3 years in India. He has completed dual masters in India and Singapore. In Singapore, he has done his Master of Science in Precision Engineering with specialization Additive Manufacturing and also Master of Engineering in Aeronautical Engineering. He has published 8 Indian patents in mechanical, aerospace and manufacturing.
Welcome to UGC series of lectures. Today we like to discuss about grain binding mechanism and process optimization for selective laser sintering. So the next bigger thing is grain binding systems. How these grains are going to bind and going to give the final product, right? So that is the different really critical area, or you can say this is you need to focus a lot on particular grain binding mechanism, because it has got 4 different methods. But you have I don't know whether you are familiarized with powder metallurgy or not. Powder metallurgy, then it is very easier. Say in powder metallurgy you have used different ways to mix up the powders. Say for example LPS, the liquid phase sintering process. There we cannot say there are 10 or 15 methods. You can list out n number of methods. Say for example you can add by say for example we have a solid powder, we can add the liquid powder in different phases. Say for example heated powder, heated liquid you can pour, or you can expose to the open atmosphere, or you can change atmosphere to argon or nitrogen or whatever. So likewise you have n number of options to get a liquid phase sintering of a powder material, right? So this are some of the areas they want to have better alloys for the upcoming products. Say for example you have heard about some of the alloys which has got n number of combinations. Say for example there is a component in a gas turbine engine, particularly they will call it as turbine inlet guide vanes. It is the one has to going to take the maximum temperature. Even some of us thinking that combustion chamber may take the maximum power, but in that particular part of the engine, this turbine inlet guide vane has to take the maximum temperature. So even after doing reverse engineering, still they couldn't find out what are all the ingredients they have added or what are all the materials they have included to get the finished product, because they have n number of alloys. One we are familiarized with is titanium. This is the one which takes the maximum temperature and withstand, and it's malleable to build up a different material. Even though that is the structure is little more complex, they don't have titanium alloy alone. They have nickel, chromium, magnesium alloys to get the finished product. So that is how they need to achieve with the help of grain binding mechanism. They need to have different alloys put together to achieve a finished product, but we need to maintain an optimum temperature to achieve it, because we need the scanning of a laser we have discussed already, because scanning we cannot keep on changing the laser intensity. So what we need to do, the intensity has to be fixed or constant, right? So this alloy has got so many materials into it. As I said, it has got nickel, chromium, magnesium, molybdenum. So likewise we have n number of materials all put together to form a single component. So this particular process is really helpful to achieve that particular components which has got n number of alloys into it. So this is one of the method is solid state sintering, right? Solid state, you are already seen many of the powders already in solid state, and we need to give compaction or being compacted in such a way that this is how the components are being merged together. You know, each and every component has its own atom. Internally we have nucleus and surrounded by electrons. Only this electrons in a solid has giving more strength, particularly between each and every atoms to bind it together. Otherwise this material become liquid, right? So this strong force of attraction already been there, but even though we need to give the input in such a way that it is being compacted by overcoming the force acting between the electrons as well. So this solid state sintering has a major, like if you are compacting the material, it needs additional energy input to get this particular process of combining this particular atoms in a compact region. Say for example this necking process. Necking is a one when two particular atoms are combining together with some additional input. Say for example additional force, might be pressure or heat, right? Only these two ways we can make it compact, right? So this is how they are making compact, and they need to have a minimum porosity, or we can say the size between the atoms should be very minimum to get a better compaction. So that they are achieving using solid state sintering process. The input is only temperature, I mean heat or pressure, right? The next way is chemically induced sintering. In this, what they are additionally doing, they are adding some activating chemicals, right, to achieve the same, but directly or indirectly we are inducing either temperature or pressure, right? These are all the ways where we can have compacted material. We don't have any other option to get compaction. So we are again introducing some chemicals which are thermally activating, right? Thermal, particularly the temperature has been activated and making the component as a compacted component. So that is they are achieving using chemically induced sintering. And third one is liquid phase sintering, that is LPS. As I said, it has got so many methods. Say for example, some solid particular material has been kept inside a container. We need to introduce some liquid. It might be a same, or might be with binder, or might be with some other atmosphere. Do you know what is atmosphere, right? Say for example, the container has been kept within a closed chamber of argon or nitrogen or whatever it may be, just to enhance the process. That's it. So likewise, we have in liquid phase sintering, we have n number of ways to achieve the particular process. One of the method is we can use complex powders, or we can have different inputs of alloys, or you can go for some binders, as I said, different atmosphere, whatever way. So the major idea behind this LPS is, say for example, bigger ones are solids, right? You can see the bigger grains, that is solids. The lines just to describe it's in a liquid phase. So both we are keeping it together to achieve the compacted output, that is the process of compaction. That's it. But what it is alternatively doing is, this liquid phase is going to be compacted, making the solid powder acting like a binder. It's keep it more compact and more compact, so that we are achieving this finished compacted product, right? And finally, this is one of the familiarized method, that is complete melting, right? Fully melting. Once you take a alloy of metal, say for example some iron or steel or whatever it may be, we need to melt it completely, and then we can remix of any other alloy, say for example magnesium or chromium, we can mix together to achieve the compaction. How? Generally we left it over a atmospheric condition. Automatically, if you want to make it as a solid, it's become solid. Or you want to achieve it in a faster way, you can do some other process of, like if you have n number of process to make it as a solid by cooling it, by condensing or whatever it may be, right? So these are all the different ways where you can achieve the solid grains with effective binding, right? Why this binding? As I said, if you got n number of binding processes to achieve it, to get a finished product with different strengths. That is a basic reason why we need to concentrate more on binding mechanism, right? This is a 4 phases. One is solid state sintering, second one is chemically induced sintering, liquid phase sintering, and fully melting, complete melting. Okay, this SLS, process optimization. These 2 slides, it's almost, I can say it is 100% particularly for a research, right? What you can do with available data at the moment, right? What are all the data we have already, and how we can achieve, or how we can go to the next stage of research, particularly in SLS and additive manufacturing. Particularly, what are all the problems we are facing in additive manufacturing, and how we can overcome it, right? That is why I name it as process optimization. How we can optimize the existing process to achieve a finished goods. Process may be like, as we seen, it's very simple, right? We have only 4 or 5 steps to achieve a finished goods. Just we are going to draw a component in using some CAD software, save it as a STL file, and giving the input to the AM equipment, that is additive manufacturing equipment, and we are going to get the finished product. That's it. Even we don't know what we are going to get at the end result, but as a researchers or as a engineers, how you can modify and how you can alternate, or say for example, I said like particularly to increase the strength of a particular point or particular unit or within a specific region, something like that. So how we can do those kind of optimizations, how we can achieve. For that, what are all the parameters is already been there, and if you play around these parameters, how you can achieve the end result, right? First step, as you know very well, the laser power. Why? Do you know the basic difference between the electron beam power and the laser power output, right? So even electron beam power is little costlier than the laser input. So that's why the EBA, we have additive manufacturing machines using electron beam, but even the laser power is comparatively lesser in terms of cost. So that is why they prefer laser power. So likewise, in laser power itself, what are all the parameters you can take, or what are all the parameters you can alter to achieve a optimized output of a component, that you can play around. Say for example, laser power, femtosecond laser, you have nanosecond laser, or you can go for pulsed lasers, or you have femtopulsed laser, you have n number of alterations. But what is the basic reason why we need to go for laser power alteration? One is, as I said, you need, yes, exactly, particularly it depends upon the structure what we need to modify. That's the basic reason why we are focusing more about laser power, right? Even if you use femtosecond laser, it's only 10 power 15th times of seconds of the pulsar on input only it will give, right? So it's very minimum time, we can just compact the material and we can save the power for a next pulse. So likewise, if you save this power, or you can give the power input, depends upon the need, obviously we can get a better product, right? That is the reason why we are going for laser power as a major optimization technique which we can achieve. And one more thing is there, we cannot go for particularly, say for example, to making a single component, we cannot go for a femtosecond laser, because generating femtosecond laser is costlier. So what we can do, we need to play around the laser, different types of lasers. Say for example, we can go for CO2 laser, comparatively much cheaper to generate, right? Likewise, we need to play around with the laser power or whatever available lasers, right? We need to optimize that one to achieve a better parameter based on the component, right? So next one is the spot size. Spot size, as I said, you can alter using the laser itself. Say for example, it's a femtosecond laser, you can make it as a minimum level. Say for example, even micron level impact you can give. Even you have heard about the area called HAZE, right? Heat affected zone, right? Heat affected zone is one of the parameter where this spot size has to be considered. Say for example, if I am giving a too much of power input, right, what will happen to that particular spot? Obviously it will affect the surrounding areas as well. Say for example, if you are keep on affecting the surrounding area, the end product won't be 100% with good quality or whatever. It maybe have the frequent probability of embedding it, right? If you are just giving too much of heat to a particular point, what will happen? It will affect the surrounding and it will give a small space. There may be possibilities of porosity. Likewise, this part size is played a vital role as well, right? So what we should do, based on the melting temperature or based on the sintering temperature, we need to optimize the laser input as well as the duration of impact, right? The spot has to, say for example, I have fixed up a spot size, say for example, it's of 0.2 micrometer, but I keep on supplying on a particular point, what will happen? Again, the heat affected zone will be comparatively much higher. So based on the requirement and the time, these are all the parameters to get a optimum sintering temperature, right? We cannot modify based upon the component requirement, but we should be careful about spot size as well and pulse duration. As I said, we have already, in general cases, we have many pulsed lasers. Pulsed lasers, in that sense, it will give the laser input only for a specific period of time. Say for example, it may be in terms of seconds or milliseconds or microseconds or nanoseconds or femtoseconds, likewise. So this pulse duration has its own impact on it. So once we are giving the required input, the pulse duration has been controlled to get a better output, right? Again, the pulse frequency, how many times it has to be impacted, right? So these are all the basic, much basic parameters related to laser to do optimization based on the component requirement, right? And next, the scanning parameters. What are all the parameters specifically related to scanning? How the scanning can do the alteration in a product, right? Particularly the scanning, very specific with scanning speed, right? We cannot scan, even we know we need to scan the entire layer, that is fixed upon, but we shouldn't scan too fast or we shouldn't scan too slow, right? Because why? As it has its own duration to give a impact on a product or impact on a particular grains or whatever it may be, right? Once we are scanning it too faster, the impact won't be even, and as well as it won't be on required paths as well. And as well, if you are too slow, again the same problem. Some may not experience the required density. So the scanning parameter, if you let's have an example of making a component with few porosities, right? Say for example, it already has its own spot. Even some of the scanning speed may have even improved the quality of the product. Do you know how? Say for example, already it has some porous in it, right? In that particular area, if you're stopping too much of time or too fast, this will again alter this, right? So even now they are trying to improve this porosity effect in a particularly product like honeycomb structures. Say for example, in honeycomb they have two layers of sheets. Internally we have very thin layer between these two. You have seen the honeycomb, right? How it looks like. So in that you can see the shape is not 100% round or 100%, it has some irregular shapes as well. So those kind of areas, if you this particularly they are making this porous effect to get a optimum output or optimum shape of it. So likewise you can play around with scanning speed as well. Scanning space, already you have seen, between consecutive layers, between each crust and then one crust and another crust. Even this crust size also, it shouldn't be too far or too less. Already it's optimized, pre-programmed, so the scanning is been done, but the space alterations you can do it or you can improve it for a betterment of it. Say for example, as I said, you need strength at a particular point. There you can have a closer spacing, right? In some places you don't want to have more strength, so you can have a space between that. So this is how the spacing also important while making a finished better products, right? And finally the scanning pattern. Say for example, why can't we scan in horizontal way as well? There is no constraints, right? So instead of scanning only in X direction, you can scan it in Y direction. Even if possible, you can scan it in Z direction as well. So likewise, these are all the areas it's even left over to the researchers now. They are scanning in 3 different axes, 3 different ways to get a better product as well. Some they are using, you have seen about the drones or small flying objects, right? They are using for a angle scanning. Particularly they are fixed in a particular angle, say for example 45 degree to the component. From that they are planning to scan, or say for example they are planning to melt the product or sinter the product. So what is the advantage in it is, we cannot have, you can see the problem as well. I'll let you know. There you can see the many properties of a product, anisotropic, isotropic, right? So those parameters can be altered or getting the better input with the help of the scanning patterns. That is a major advantage of it. Again, the powder related parameters, mostly the powder related parameters we discuss, particularly the grain shape, grain size, grain distribution, powder density and layer thickness, material property. Powder density, again you know, say for example if you are mixing 2 or more powders to it, right? As I said, magnesium, chromium, it has got own density difference, right? How you are going to match? That is again a problem, right? you need to match and get an optimum density. That density has to be considered as an input to this powder bed, right? So likewise, you can play around with the parameters available here to have a better output, right? Again, temperature related parameters. Powder bed, you have seen we need to have a minimum temperature to maintain it before it's going to melt. That is the maximum sintering point temperature we are going to use in a powder bed. But even we shouldn't go to the maximum level of sintering as well. If you go for a maximum level of sintering, again the powder almost become compact. We don't know, even if you are applying a small temperature, it becomes solidified very easily. Even we shouldn't do that one as well. So we need to have an optimum temperature even in the bed to achieve a better product. You can say just below sintering as well, right? Then only the powder it is in the same state, right? So once the laser power is given, our laser through the laser power we are giving the temperature or to get the heat to get a better compaction and get a finished goods. So likewise, these are all the parameters where we can play around with different levels. Powder feeder, have you seen the roller, right? One roller is moving and the feeder is moving. Even you can have little temperature over there, because once what will happen if you keep on heating a product at a particular place? What will happen? Say for example, in a particular point you are keep on giving more and more temperature. There may be possibilities of sintering. So and also uneven distribution, that is a problem. Have you noticed, right? So for example, I cannot give temperature from all the 4 sides evenly to achieve it, right? Say for example, from the bottom I can supply heat. It may not reach the top surface in a particular time period. It may reach after say for example, for some 5 seconds or 10 seconds, it may reach the top level with the input temperature. Say for example, I am giving 100 degrees Celsius from the bottom, but before reaching the top, might be one layer has been removed. Consider in another way, you are keep on giving 100 degrees Celsius at the bottom. Top layer may have 5 degrees or 10 degrees. Bottom layer may have 80 degrees or 90 degrees. So that is also we cannot achieve the proper optimum. So that's why we are playing around the temperature between these 2 areas. One is the powder feeder and as well as the powder bed. So likewise, we can play around the basic temperature and we can achieve the better result. And you can see most of the systems are like open loop. Open loop, mostly they are doing it in an open atmosphere. We cannot say every time the temperature remains constant until the process is going to complete, right? In a 24 hours a day, say for example, I need 24 hours to complete a product. We cannot say all the 24 hours we can achieve the same temperature or the particular climatic condition, right? So what we need to do, we need to have a closed atmosphere, or we need to have a temperature uniformity. Even you have temperature measuring equipment in and around of the entire working area, but still we couldn't achieve the temperature uniformity throughout. So that's why they are planning to have a closed chambers. As I said, they are introducing argon environment or nitrogen environment to achieve a better finished product, right? So these are all the 4 parameters you can really work with and you can optimize the SLS machine.
There are some applications in bimetals.
Bimetals. Okay.
For example, bimetal plates.
Bimetallic strips or whatever.
Is that possible in SLS?
That's what the research as I open to you, like you can do it by changing the laser intensity at a particular point. Say for example, you are using bimetals using copper and molybdenum or copper and nickel. Particularly while scanning the copper part or nickel part, you need to use a different laser power, and again here the nickel copper part different laser power input, and for nickel part you can use different power input, so that you can optimize and you can have it. That's what, again the scanning direction you can change it, like X instead of X or Y, but you need to play around because we are giving the single input at the moment. We are giving only one STL file. It doesn't know whether it is a nickel or copper or whatever it may be. How we need to, that's what we need to optimize and we can achieve it. That is possible only by changing the input of the laser power.
One more question.
Yeah.
There are some cutting tools. For example, tungsten carbide.
Okay.
It is manufactured by powder metallurgy process. Could we achieve that kind of HRC, hardness,
Hardness
in this SLS process?
That's what, again, it's all our in a research area. You can achieve, but we need to play around the parameters and as well as the input of alloys. If you have tungsten and carbide, only the two inputs, but it need to be achieved in a particular fashion. What I said, at a particular point you need to increase the intensity of the laser beam so that we can have better hardness at a particular point. As I explaining to you about the cup, only at a particular point we need more strength, but here throughout you can have the whole strength. It can be
achieved.
Yeah, but till now we don't have machines to achieve 100% as you need. There are researchers still they are doing, but you can achieve.
In biomedical,
okay,
bone, teeth are in solid conditions.
Yeah,
there are some organs in semi-solid conditions.
Yes.
Could it be possible in SLS?
That's what they are doing at the moment. As I said, the company Argonova, they have built two different, like here we have centering, right? Similarly, we have a process of curing it, right? What they will do, say for example, I have a problem with the skin. One layer has been gone, but it protruded in my bones as well. I need to have all this process achieved in a single process, but that is little harder at the moment. But what they are doing, initially the bone curing done with a different mechanism, it's like a printer.
Yes.
Directly it is printing with the hardness of particular requirement of the bone, and same printer change it by giving the different input of tissues. They are printing the, as we have different layers, epidermic, endodermic, or whatever may be the skin surface, accordingly they are changing it. Okay. Now they are achieving based on that.
Compacting, I was telling about compacting.
Yeah.
Well, telling about compacting, we should give additional pressure.
That's what. Compacting can be achieved using pressure or temperature. Both are, if it is in a closed atmosphere, almost like, even if you are, say for example, if I am compacting, obviously that will be raising pressure, raising temperature as well. Because in a closed atmosphere, both are directly proportional. We cannot achieve increasing the pressure and reducing the temperature. That is not possible in a closed atmosphere. Obviously, both work together.
We are designing or modeling a component in 3D modeling.
Okay.
After finishing in this SLS,
okay,
the same dimension, will we get the same dimension?
Dimension at the moment we can achieve 100%. We can even, you can say, without tolerance we can achieve. That is possible.
Okay, thank you.
Maybe now, instead of, generally in machining process we have a tolerance of 0.01 mm or something like that based on the component. That is based on the component will keep on changing. But here, if we are giving 100% input, we can achieve maximum zero tolerance we can achieve. Those kind of machines are available at the moment. As I said, the GE fuel nozzle, right? They have achieved 100%.
Okay. While sintering, there is a shrinkage in...
Possibilities are there, for sure.
Okay.
100% there is a possibilities. But that's what, the optimum temperature while manufacturing and the atmosphere where they are manufacturing also matters. We cannot achieve, say, some atmosphere, the material has good strength. Even if you're changing to the normal atmosphere, there may be possibilities of change. So what they are doing, they are maintaining the atmosphere as well until the finished product comes out. As I said, they are introducing a nitrogen atmosphere to the entire machining unit, so that there may be possibility, there won't be any chances of cross mixing of other materials or any, say for example, any dust or whatever it may be. So they can achieve the 100% optimized output. That's why the fuel nozzle is the best example, as you are asked for, they can achieve. In this session, we have discussed about grind binding mechanism and process optimization for selective laser sintering. Thank you.